Hey guys, Dr. Thomas. This is the first video for Chapter 9. I tried to make the video in the classroom, but that video can't be posted, so I'm making it again from home. So we're starting the section about VSEPR theory, which is valence shell electron pair repulsion theory. It's the general idea from which all of the shapes that we have for different molecules can arise from. It's really important. It gives us an idea of what molecules look like. And then as we go through this material, key here is it's going to get us to this idea of polarity, deciding whether molecules are polar or nonpolar, but that will probably be in the second video rather than the first one. So I'm going to scroll through. General information, what VSEPR is important for determining the properties of compounds. There's our acronym and what it stands for. When we draw Lewis dot structures, we are focused on valence electrons only, which are the ones in the highest shell. We kind of ignore all the core electrons because they are not involved in bonding. And when we do this, we're specifically looking at nonmetals and forming covalent compounds or polyatomic ions. Okay, our big concept here is that electrons repel each other. So while electrons do pair up in orbitals, the electrons in one orbital want to be as far away from the electrons in another orbital as possible. So if we are drawing a Lewis dot structure and we want to actually understand what the shape looks like, the idea is the electrons repel each other. They go as far apart as they can, and then we can measure the distance between groups based on the angle between them. So I'm going to draw a quick molecule on my dry erase board. So if I have carbon dioxide, which carbon dioxide has a carbon atom with a double bonded oxygen. Oxygen has 2 lone pairs. But then the other oxygen atom is coming off the carbon, wants to be as far away from this oxygen as possible. So if I put the other oxygen right here, going straight up, then basically I could determine how far this oxygen and the double bond is from the other one, based on the angle. Okay, if I put this one vertical and that one's horizontal, that would be like a 90-degree angle. That's not the best spacing that's possible. If I only have 2 groups around the center atom, they're going to go to opposite sides. So it makes sense that my other oxygen is going to be as far away from the other one as possible, and it's going to give me what we would call, from the carbon, 2 oxygens are on opposite sides. That is going to be a linear molecule. So that the word linear represents the shape of the molecule, as opposed to if I had drawn it and put the 2 oxygens kind of off at some other angle like that, that would be what we call a bent molecule. Okay, for CO2, this is the best spacing, so that would be an incorrect structure to draw. Okay, if I go to larger numbers of groups around the center atom, then I'm going to get different shapes that can come up. So let's say I have the BF3 molecule, the boron. It has 3 fluorines and no lone pairs. The 3 bonds to the fluorines are going to be as far apart from each other as possible. So the 3 fluorines are going to go out. Of course, each fluorine should have its 3 lone pairs. So if I fill all those in, I can measure like the 3 fluorines to be as far away from each other as they can be. They're going to spread out in a circle, and around the circle is 360 degrees. So if I'm dividing into 3 angles, that's going to be 120 degrees right there, 120 degrees right there, and 120 degrees right there, if everything is evenly spaced out and spaced as far away from each other as they can. Okay, the name of this shape, the 3 fluorines are forming a triangle, and the molecule is flat, it's in a plane, so that we call this shape trigonal planar. Okay, there are a bunch of shapes that we need to learn the names of. So as we go, there's a chart in the book that lists all the possible, what we call electron geometries, and at some point you're going to have to memorize those. In a normal semester, when you take the test, you have to know all those by heart. For you guys, you're going to have open book test, so you're going to be able to look at the chart in the book as you take the test if you want to, but just realize that when it comes to 1212 and organic, at that point you're going to need to know those shapes anyway. So at some point you got to learn them. You may as well go ahead and do it now. Anyway, so we want to maximize the angle between the groups to reduce the repulsion between atoms. Okay, so we're going to get a certain set of shapes that are based on the number of electron areas around the nucleus. Sometimes those are called electron domains. Sometimes we refer to, if you count the electron domains, the actual number you get, it's called the steric number. Okay, steric is S-T-E-R-I-C. So there's several different words that can be used by different books and worksheets and websites, so just be aware. But if the number of groups corresponds to a shape, if carbon has two things around it, they go to opposite sides, that two groups corresponds to a linear shape. If you have three groups around an atom, they're going to go to trigonal planar. Those are the ones that I already demonstrated. Okay, if you go to 4, 5, and 6 groups, at that point you're going to get tetrahedral, trigonal bipyramidal, and octahedral as your shapes that we get. Okay, and yes, at some point you have to memorize those names. Now, what are the groups that I'm talking about? The groups around a center atom can be a bond to another atom. Now that bond might be a single bond, a double bond, or a triple bond. Regardless, that counts as one group. And then also lone pairs. So when I look around an atom, like if I draw a water molecule, it's got an oxygen in the middle, the oxygen is connected to two hydrogens, and it has two lone pairs on the oxygen. So that's two bonds plus two lone pairs, makes four groups. Since the oxygen has four groups around it, those four groups are going to spread out in a certain way around the oxygen atom, and the shape that corresponds to that is called tetrahedral. Okay, so here's our list. If we have two groups coming off a center atom, so in this picture the center atom is right in the middle, and then one group goes to one side, the other group goes to the other side. The shape that corresponds to that is linear. The bottom's a typo, so ignore the trigonal plane right there. That shouldn't be on this slide. And then our angle between the two groups, if it's linear, will be 180. Okay, so all this is in the PowerPoint. You go to 3 groups, we get trigonal planar. Go to 4 groups, you get tetrahedral. Now tetrahedral is the first shape that we see that's actually three-dimensional. So if you look at these pictures, hopefully you can tell that they are not flat molecules. They actually extend in all 3 dimensions. So in this structure right here, the bond in the front at the bottom is actually coming out of the screen towards you, and the one pointed to the left is actually going behind the screen. So it's very important to recognize the three-dimensional structure there. Okay, when you go to 5 groups, we get trigonal bipyramidal. Now that name is very complicated, but the idea of it is that in the center of with 5 groups, 3 of the groups form a triangle around the center atom that are flat, horizontal, and then I have one atom coming up and one atom coming down. So those 5 groups, I could say that there's a triangle in the middle. If I were to close a structure from the middle triangle up to the top, it forms a pyramid on the top. But then I can do the same thing going to the one on the bottom. So it's a triangle in the middle with a pyramid on top and bottom. So that's the trigonal bipyramidal. The angles that we get, you get in the triangle, we get 120 all the way around the triangle. Then from the horizontal triangle to the top, it's gonna be perpendicular, so a 90-degree angle. And then you actually get one more that's not in this PowerPoint. From the top all the way to the bottom, that would be an angle of 180. So there are actually 3 different angles that come up with trigonal bipyramidal. Finally, we get octahedral. This one we kind of have a square in the middle of the molecule, plus one on top, one on bottom. So in this one, the angles that we get are 90 degrees between any 2 groups, and then if I go from top to bottom, that would be 180. So those are the 2 angles that correspond to octahedral. Now, keep in mind, 6 groups gives us octahedral. I know that octa means 8, but that's a 3-dimensional structure. If you take the 6 corners and close in to a solid structure, it would be a geometric figure with 8 sides. It has 6 vertices, but 8 sides. So that's why it's called octahedron. But just stick with 6 groups is octahedral. Now, once we cover the basic shapes, then we have to realize that those basic shapes that we've already covered are the foundation for what the molecule looks like. But most of the time when we draw a molecule, we focus a lot more on the atoms than the lone pairs. Okay, so we're going to distinguish two things. It's going to be what we call the electron geometry and the molecular geometry. Okay, the electron geometry is going to include all the electron groups around the center atom. And the molecular shape, or the molecular geometry, we're going to take the lone pairs off and see what the shape looks like without the lone pairs. Okay, so there is going to be a separation. There's two types of shapes that we need to learn. Okay, so I'm going to show those in just a second. So if I have three groups, how could I have three groups? Well, the top row of this table assumes the first number is the number of bonded atoms. The second number is the number of lone pairs on the center atom. Okay, so if I have a center atom that has three bonded atoms and no lone pairs, then the molecule is going to look like this, and three groups is always trigonal planar. If I say, what's the electron geometry? That's the overall structure where I look at everything. So this one, the electron geometry, is trigonal planar. But then if I say, okay, now take off the lone pairs, well, since this one has no lone pairs, if I ask you for the molecular geometry, which is the shape without the lone pairs, this one will be the same. So the electron geometry and the molecular geometry will be identical to each other. They're both trigonal planar. Okay, but then if I go down to the molecule below, which an example for this one would be the nitrite ion, NO2-. If you draw it out, I have the nitrogen in the middle, I have the bonds to the two oxygens. Again, remember that double bond is actually shared between the two oxygens through resonance forms, so they're actually equivalent to each other. But then the nitrogen also has a lone pair. That lone pair is in an orbital that the three groups, oxygen, oxygen, and lone pair, they have to spread out into the triangle. So the electron geometry, which is the overall arrangement of electrons, is going to be trigonal planar. But then if I take off the lone pair, that leaves an atom in the middle with two other atoms connected, and they're not linear. So that molecular shape we're going to call bent. Okay, the molecular shape or the molecular geometry is what the molecule looks like without lone pairs. So the lone pair is there, but we're going to cover it up. We're going to pretend it's not. Then we look at the overall shape, and there's a name that corresponds to it. So from the electron geometry of trigonal planar, there are two possible molecular shapes. It can remain trigonal planar, or it can become bent. Then we go to the next electron geometry. If I have four groups, if they're all bonds, then my electron geometry and molecular shape are the same. If it's three bonds, one lone pair, my molecule is going to look like that one. If I cover up the lone pair, that's where the molecular shape of trigonal pyramidal comes from. And then if I have two bonds and two lone pairs, I can cover those up. It's going to be a tetrahedral electron geometry, but it's going to be another bent molecule that I get right there. Okay, so for each number, there's a set of shapes you have to learn. For 5, that's electron geometry, trigonal bipyramidal. But then as I vary the number of lone pairs, I can have trigonal bipyramidal, seesaw, T-shaped, and linear are the possible shapes that I can get from that. Okay, and then finally for 6, again, there are several shapes I can get, so you have to learn those. Okay, so that's going to be it for this section. We'll pick up again with Chapter 9, Part 2 video. Thank you.